In 1906, Charles Sherrington, who was basically one of the absolute titans of neurophysiology.
Oh, without a doubt, a total legend.
Right. Well, he made this really bold, almost heretical claim at the time. He stated that the simple reflex, the very thing we routinely test in the clinic with a reflex hammer, is actually a convenient fiction.
Yeah, a convenient fiction. It's such a great phrase.
It really is. And welcome to our deep dive. If you're just joining us today, we are embarking on something massive. We're officially kicking off our 9-part series dedicated entirely to Part V of Eric Kandel's Principles of Neuroscience.
The definitive text.
The absolute Bible of the field.
Yeah.
And we are focusing relentlessly on the neuroscience of movement. Now, I want to speak directly to the listener I know is out there right now.
Yeah, we know exactly who you are.
We do. You are a neuroscience PhD student.
Yeah.
You're probably currently behind the wheel of your car, navigating traffic, and you're using this transit time to synthesize the material in Chapter 32.
Which is a dense chapter.
Oh, incredibly dense. So our mission today is to completely deconstruct sensorimotor integration in the spinal cord. And because the Kandel text is just packed with electrophysiological data and anatomical circuitry, we are going to pace this session very deliberately.
Right. Unhurried. Sem pressa, as they say.
An unhurried approach. We'll provide all the rigorous mechanistic depth that your doctorate demands, but we're going to weave in enough conversational breathing room so you can safely process all this biophysics.
While keeping your eyes on the road. Please keep your eyes on the road.
Yes, very important. So let's unpack Sherrington's provocation. Because culturally, I think we tend to view the spinal cord as almost like a biological extension cord.
Yeah, just a thick bundle of wires.
Right, just passively shuttling upper motor neuron commands down to the periphery and then sending afferent data back up. But Sherrington was hinting that the spinal cord is actually a highly sophisticated coprocessor.
It is. I mean, it operates with immense local autonomy. Sherrington wasn't denying the actual, anatomical existence of reflex arcs. He was pointing out that in a living, behaving organism, the central nervous system never allows a reflex to just operate in an isolated vacuum.
It's always being tweaked.
Exactly. Every single movement, regardless of how voluntary or cortically driven it feels to you, it relies continuously on this invisible regulation by incredibly complex spinal interneuron networks.
So the cortex doesn't just dictate kinematics in a vacuum.
No, not at all. It basically negotiates the execution with the spinal cord. And the spinal cord is constantly integrating this massive influx of peripheral telemetry.
Right, the sensory feedback. And that reframing is really central to this entire 9-part series we're doing. The isolated reflex is basically a laboratory artifact.
A very useful artifact, but still an artifact.
Yeah. But to understand how it's modulated, we first have to understand the baseline circuitry, right? So let's start with the architecture of the stretch reflex, the myotonic reflex.
The classic.
The classic. So we know the sensory signal originates in the muscle spindle when the muscle is lengthened, and it travels via those large diameter afferent fibers. And since we're dealing with fibers conducting at, up to 120 meters per second?
Yeah, incredibly fast.
The latency of this circuit is just famously brief.
It is. And the temporal constraints of this circuit are actually what initially allowed physiologists to map it out. Because when the afferent enters the dorsal horn, it does something that's statistically pretty rare in the CNS.
It skips the middleman.
Exactly. It forms a direct excitatory connection with the alpha motor neurons in the ventral horn, the ones that innervate the homonymous muscle, the exact same muscle that was stretched.
And when we measure the delay between the afferent volley arriving in the cord and the efferent motor signal leaving, it clocks in at roughly 0.7 milliseconds.
Right, roughly 0.7. And given that a single synaptic cleft requires about 0.5 to 0.9 milliseconds just for vesicle fusion and neurotransmitter diffusion.
The math is perfectly rigid.
The math is absolute. There is physically no time for an interneuron to be involved. It has to be monosynaptic.
Wow. Okay, so the afferent also branches to excite synergistic motor neuron pools, right? To ensure the whole functional muscle group resists the stretch.
Yes.
But a unilateral contraction creates a massive mechanical conflict. I mean, if my biceps reflexively contracts to shorten, my triceps, the antagonist, has to yield.
Right, they can't both fight at the same time.
Exactly. If the alpha motor neurons for both pools fired simultaneously, the joint would just lock up into a rigid spasm. So the afferent has to silence the antagonist pool too.
And it does that through a parallel polysynaptic pathway. This is where the afferent inhibitory interneuron comes in.
Okay, break that down for us.
Sure. So the electrophysiological signature of that parallel pathway is very distinct. If you record the inhibitory postsynaptic potentials, the IPSP, and the antagonist motor neurons, the latency jumps up to about 1.6 milliseconds.
Ah, so the original 0.7, now it's 1.6.
Exactly. That additional 0.9 milliseconds is the exact temporal footprint of a second synaptic delay.
That is so elegant.
It really is. It confirms that the eye afferent first synapses onto the eye inhibitory interneuron, and then that interneuron projects to the antagonist motor neuron, releasing glycine to hyperpolarize it.
So this whole architecture, the excitatory drive to the homonymous pool and the inhibitory drive to the antagonist, this is the bedrock of reciprocal innervation.
100%. It's how we move without fighting ourselves.
Right. But, knowing that architecture is one thing, proving it intact, living humans without using invasive spinal recordings, that required immense methodological creativity.
Oh, absolutely.
Which brings us to Paul Hoffmann's technique from the 1950s, the H-reflex.
Yes, the H-reflex, it's an absolute staple in clinical neurophysiology.
Because it fundamentally allows us to probe the excitability of the motor neuron pool by bypassing the mechanical muscle spindle entirely.
Yeah.
Right? By using transcutaneous electrical stimulation.
Exactly. Hoffmann's setup is just brilliant in its simplicity. You take a stimulating electrode and you place it over a mixed peripheral nerve. Let's say the tibial nerve in the popliteal fossa behind the knee.
Okay.
And you record the EMG activity over the target muscle, like the soleus and the calf. Now, because the eye afferent fibers have the largest axonal diameter, they actually have the lowest electrical threshold.
Which feels counterintuitive to a lot of people.
Right. But physics dictates that the larger the axon, the less current you need to depolarize it. So they have a lower threshold than the slightly smaller alpha motor axon.
Okay, so for our driving PhD student, let's visualize this. You apply a very low-intensity stimulus. You selectively recruit the eye afferents. The action and potential races orthodromically, meaning in the normal, correct direction up to the spinal cord.
Right.
It crosses the synapse, triggers the alpha motor neuron to fire back down to the muscle. And on the EMG, you see this delayed electrical wave.
That's the H wave, the purely reflexive response.
Got it. But as you dial up the stimulus intensity on the machine, the electrophysiology gets deeply interesting.
It does, because as the current increases, you eventually surpass the threshold for the efferent motor axons themselves.
The ones going straight to the muscle.
Exactly. Now, the stimulus is directly triggering action potentials in those alpha motor nerve fibers. And since this signal travels directly down to the muscle without needing to take that long trip up to the spinal cord and back.
It arrives super fast.
Very fast. And this appears on the EMG as the early M wave, M for motor.
Okay, so as you continue to crank up the voltage, the M wave grows, because obviously you're recruiting more motor units directly from the shock.
Right.
But counterintuitively, the H wave begins to shrink. And at supramaximal stimulation, the reflex completely vanishes. The H wave just drops to zero.
It disappears.
And for a student analyzing raw EMG data, understanding the biophysics of why that reflex disappears is critical, because it all comes down to antidromic collision.
Yes. Antidromic collision. It's a beautiful concept. The biophysics here rely on the absolute refractory period of the axonal membrane.
Right, the sodium channels get locked.
Exactly. When you apply a massive electrical shock to the mixed nerve, you trigger action potentials in the motor axons that actually propagate in both directions.
Because you're stimulating it in the middle of the nerve.
Right. The orthodromic wave travels down to the muscle normally, generating that massive early M wave. But an antidromic wave travels backward, up the motor axon, toward the spinal cord.
Okay, but simultaneously, that exact same high-intensity shock also recruited every single eye afferent, right? Sending a massive sensory volley to the cord, which in turn causes the alpha motor neuron to fire its orthodromic reflex signal back down that exact same motor axon.
Precisely. So picture this. You have the reflexive orthodromic action potential speeding down the axon from the spine, and the artificial antidromic action potential speeding up the axon from the site of the shock.
They meet.
They meet, and they collide. And because each action potential leaves this wake of inactivated, voltage-gated sodium channels behind it, neither signal can pass the other.
They just annihilate each other.
They completely wipe each other out. The reflex signal never reaches the neuromuscular junction, which is exactly why the H wave is completely obliterated at high stimulus intensities.
Man, that collision principle is just such an elegant piece of physiological logic.
It really is.
But let's take a breath here and circle back to Sherrington's whole fiction concept.
Yeah.
Because we have this hardwired, highly predictable latency arc. But if you hit a pothole while driving right now...
Which hopefully you don't.
Right, hopefully not.
Hopefully.
But if you do, the reflexive contraction in your arms to stabilize the steering wheel, it isn't just a blind, rigid loop.
No, not at all.
The gain of that reflex is already pre-tuned by the motor cortex, based on the velocity of the vehicle, your posture, everything. And to understand how the brain modulates that reflex, we really have to look past the spinal circuitry for a second and examine the actual high-definition sensory hardware embedded in the muscle belly itself.
Oh, the muscle spindle. The telemetry provided by the muscle spindle is staggering in its resolution.
Yeah.
And the mechanical reality that dictates how it functions is its anatomical alignment. The muscle spindle is encapsulated, and it sits perfectly in parallel with the force-generating extrafusal muscle fibers.
Okay, so it's parallel. Why is that important?
Because it's anchored to the connective tissue running right alongside the main muscle mass, any change in the length of the whole muscle imposes the exact same mechanical deformation on the spindle.
Okay, so to give our driving listener a quick mental model.
Yeah.
If the main extrafusal muscle is a thick bungee cord, the spindle's like a tiny, fragile rubber band taped right beside it. They stretch and slacken together.
That's a perfect analogy. But the spindle isn't just measuring absolute static length. It's actually capturing complex velocity derivatives.
It's doing calculus.
It literally is. And to achieve that, the intrafusal fibers, the fibers inside the spindle itself, are structurally heterogeneous. They aren't all the same. We have nuclear bag fibers and nuclear chain fibers.
Right. And the nomenclature there just reflects the distribution of the myonuclei in the non-contractile equatorial region, right? The center of the fiber.
Exactly. In bag fibers, the nuclei are clustered together in this swollen central region. It looks like a bag, and bag fibers are further differentiated into dynamic and static types, which have totally distinct viscoelastic properties.
Okay, how so?
Well, the dynamic bag fibers have a highly compliant central region, but very stiff polar ends.
Got it.
Chain fibers, conversely, have their nuclei aligned in a single file, like a chain, and they possess a much more uniform elasticity across their entire length.
And the sensory innervation wrapped around these structures is what dictates the actual afferent signal profile, right? The primary endings, the massive IA afferents we just discussed, they spiral around the equatorial region of all three types. The dynamic bag, static bag, and chain fibers.
Right. And the mechanical properties of the dynamic bag fiber are what grant the IA afferents its explosive sensitivity to velocity.
Because of that compliance center.
Yes. When the muscle is subjected to a rapid stretch, that highly compliant central equator of the dynamic bag stretches instantly. It stretches before the stiffer polar ends can yield.
So it snaps open.
It snaps open.
Yeah.
And this rapid mechanical deformation forces open the mechanically dated ion channels in the IA terminal, resulting in this frantic, high-frequency burst of action potentials.
And that's the dynamic response.
That's the dynamic response. It is signaling the precise rate of change in muscle length. How fast is it stretching?
But we also have the secondary endings, the type 2 afferents, and they don't wrap around the dynamic bag fibers, do they?
No, they don't. They primarily innervate the static bag and the nuclear chain fibers, and they typically attach juxta-equatorially, meaning just off-center.
Right. And because the chain fibers stretch much more uniformly, without that initial equatorial snap, the type 2 endings are relatively insensitive to the speed of the stretch.
Exactly. They provide a steady, tonic firing rate that corresponds directly to the absolute resting length of the muscle.
The static response.
The static response.
So it's basically the difference between a speedometer and an altimeter on an airplane.
I love that analogy.
Yeah, right. The IA afferent is the speedometer.
Yeah.
It's screaming about how fast the altitude is dropping, allowing for rapid reflexive corrections. But the type 2 afferent is purely the altimeter. It's just reporting the current altitude.
Which is absolutely essential for the brain's continuous mapping of joint position and static posture. You need both pieces of data.
You do. But let's pause here. Because if you think about it, there's a massive physiological flaw in this parallel arrangement.
Oh, there is a huge mechanical problem.
Right. If an external force stretches the muscle, the spindle stretches, and the afferents fire perfectly. But what happens during a voluntary contraction? When my upper motor neurons drive my alpha motor neurons, my extrafusal muscle shortens.
Yeah.
Because the spindle is in parallel, it should theoretically just go completely slack.
It would crumple. It would be totally useless. If the system relied solely on alpha motor neurons, the moment the muscle shortened, the tension on the equatorial region of the intrafusal fibers would drop to absolute zero.
The mechanically gated channels would close.
They'd snap shut. And both the IA and type 2 efferents would fall completely silent. The sensory telemetry would be totally unloaded during the exact moment of active movement.
Which is arguably when the central nervous system needs kinematic feedback the most. I mean,
Wow.
flying blind during an active contraction is an unacceptable vulnerability for an organism.
It's a recipe for disaster. So the evolutionary solution to this is the fusimotor system, specifically the gamma motor neurons.
Ah, the gamma motor neurons.
Right. So while alpha motor neurons innervate the massive extrafusal fibers to generate force, the much smaller gamma motor neurons innervate the striated polar ends of the intrafusal fibers themselves,
Inside the spindle.
inside the spindle. And this leads to the mechanism of alpha-gamma coactivation. When your motor cortex issues a command to contract a muscle, it doesn't just drive the alpha pool, it simultaneously sends a descending parallel drive to the gamma pool.
Okay, so as the main extrafusal muscle shortens, the gamma motor neurons cause the polar ends of the intrafusal fibers to actively contract as well.
Exactly. And because the poles pull away from the center, this internal contraction reels in the slack. It keeps the central equatorial region perfectly taut, even as the whole muscle gets shorter.
That is amazing. By maintaining that tension, the mechanically gated channels remain physically distorted, and the IA and type 2 afferents continue to fire.
The spindle stays online.
It stays online. But, reading through the candle text, it emphasizes that this isn't just a crude mechanism to prevent slack. It's not just an on-off switch.
No. The nervous system can modulate the dynamic and static gamma motor neurons completely independently.
To change the gain.
Yes, to aggressively alter the gain of the sensory feedback based on the specific behavioral context. It's a profound example of top-down sensory modulation.
Okay, so give us an example.
Well, if the descending pathways selectively increase firing in just the dynamic gamma motor neurons, they specifically increase the stiffness of the polar regions of the dynamic bag fibers.
Which hypersensitizes the afferent to velocity.
Exactly. The
Yeah.
spindle becomes this hyper-alert trigger wire. It's primed and ready to fire a massive burst of action potentials at the slightest unexpected perturbation.
To ground this in experimental reality for our listener, we absolutely have to talk about Arthur Prochaska's phenomenal chronic recording experiments.
Oh, the awake behaving cat experiments. Legendary.
Legendary stuff. Recording spindle afferent activity during unconstrained movement is technically staggering to pull off. But the data completely revolutionized our understanding of this fusimotor system, right?
It did. Prochaska's data proved definitively that gamma drive is tightly coupled to the predictability of the environment.
Okay.
So when the cat was simply sitting around or performing highly predictable, slow movements like just walking on a flat, wide surface overall gamma activity remained relatively low.
Because the nervous system doesn't require hyper-resolution feedback for stable, easy tasks.
Exactly. Why burn the energy? But when he took those same cats and placed them on a narrow, elevated beam,
Or they have to balance carefully.
right, an environment requiring precise balance where a single misstep meant falling, the electrophysiology shifted dramatically.
What happened?
In that unpredictable, high-stakes environment, Prochaska recorded a massive, sustained increase in both static and dynamic gamma activity.
So the central nervous system intentionally cranked up the gain on the muscle spindles.
It turned the dial all the way up. By maximizing that dynamic gamma drive, the brain ensured that if the cat's paw slipped even a fraction of a millimeter,
The eye afferents would instantly trigger a powerful compensatory stretch reflex.
exactly, to correct the limb before the center of gravity was totally lost.
Wow. So the brain is actively predicting the sensory requirements of the immediate future and tuning the local spinal hardware to meet them.
It's a beautiful division of labor. The cortex dictates the strategic parameter like maximize stability, and the local spinal circuits execute the tactical firing rates.
That's incredible.
Oh.
But as sophisticated as the spindle is, it only measures length and velocity.
That's true.
And if our driving listener reaches over right now to pick up their travel mug, length data isn't enough to prevent them from either dropping the mug or crushing it, right? They need high-fidelity telemetry regarding the actual physical force, the active tension being generated.
Right. And to get that, we need a completely different class of sensor, the Golgi tendon organ, or the GTO.
Okay, let's get into the GTO.
So the anatomical positioning of the GTO is what dictates its mechanical function. Unlike the spindle, which we said is in parallel, the GTO sits tightly in series with the extrafusal muscle fibers.
Meaning it's at the end of the line.
Exactly. It's embedded directly in the musculotendinous junction. Therefore, any contractile force generated by the muscle fibers must physically transmit through the tendon to act on the bone.
Which means 100% of that active tension passes directly through the GTO.
And 100% of it. And the internal architecture of the GTO is remarkably elegant. It consists of a collagenous capsule containing these intricately braided collagen fascicles.
Like a woven rope.
Like a woven rope. And interwoven right through this rigid collagen matrix are the unmyelinated terminal branches of the IB's sensory afferent.
Wait, not IA.
Right, IB. Spindles are IA, GTOs are IB.
Got it.
So when the muscle actively contracts, it places tension on the tendon, causing those collagen braids inside the GTO to stretch and straighten out.
And as they align, they physically squeeze the nerve endings.
They pinch them. They literally physically squeeze and pinch the epiphytic terminals that are trapped between them. And this pinching distorts the axonal membrane, opening mechanically gated ion channels and triggering action potentials.
So the harder the muscle pulls, the tighter the braids pinch, and the faster the A to Trent fires.
Exactly. It's a direct physical translation of force into electrical frequency.
Okay, I want to explicitly clear up a historical misconception here, because this is something that still lingers in a lot of older curricula and undergrad textbooks.
Oh, the emergency brake myth.
Yes. Early physiologists noticed that when the afferent fired, it entered the spinal cord and synapsed onto the inhibitory interneuron, which then suppressed the alpha motor neurons of that exact same contracting muscle.
Autogenic inhibition.
Right. And this led them to conclude that the GTO was just a high-threshold emergency brake, like a safety switch designed to force you to drop a massive weight before your tendon literally avulsed from the bone.
Which makes sense intuitively, but that dogma has been entirely overturned by modern microelectrode recordings.
Completely overturned.
The GTO is not a high-threshold safety device. It is an exquisitely sensitive, low-threshold force transducer. I mean, the firing of even a single motor unit, just a few individual muscle fibers, is enough to generate sufficient localized tension to trigger afferent firing.
So it's not waiting for a catastrophic load.
Right.
It's constantly active during the lightest, most delicate manipulations.
Exactly. The autogenic inhibition serves as a continuous negative feedback servo mechanism.
Like cruise control.
Yes. Operating much like a cruise control system for muscle tension. If you're holding a fragile object like an egg, the brain sets a target force. As your grip tightens, the GTOs detect the rising tension.
And the increasing afferent activity drives the inhibitory interneurons to gently apply the brakes to the alpha motor neurons.
Right. It smooths out the recruitment of motor units, it prevents forced tremors, and ensures the tension remains perfectly locked onto the target parameter. You don't crush the egg, but you don't drop it either.
It's a beautiful system for fine motor control. But it creates a glaring mechanical paradox for gross motor output.
It does.
Let's say you're at the gym. You're attempting a maximal deadlift. Your leg extensors are generating astronomical amounts of force. According to the architecture we just described, your GTOs should be firing at absolute maximum frequency.
They would be screaming.
Right. Driving the inhibitory interneurons to completely shut down your quadriceps. The autogenic inhibition should cause your legs to instantly buckle. So how do we ever lift anything heavy if our own spinal cord is hardwired to inhibit the contraction?
That paradox perplexed neurophysiologists for decades, until they discovered one of the most sophisticated mechanisms in the central nervous system, state-dependent reflex reversal.
Reflex reversal. This is the software update.
It literally is a software update.
Yeah.
The physical wiring of the spinal cord is stable, but the physiological routing of the signals is deeply plastic. The spinal cord dynamically remaps the reflex pathways based on the behavioral state of the organism.
Let's break down the biophysics of this, specifically during locomotion. Because walking is divided into the swing phase, where the leg is airborne, and the stance phase, where the foot strikes the ground and bears the full weight of the body.
Right. So during rest or non-weight-bearing tasks, the GTO reflex operates exactly as that servo mechanism we described earlier. The afferent excites the IB inhibitory interneuron, suppressing the extensors.
The normal brakes.
Normal brakes, however. The millisecond the central nervous system initiates the stance phase of locomotion. Specialized spinal circuits known as central pattern generators, combined with descending brainstem drive, send a massive neuromodulatory wave into the interneuron pool.
They fundamentally alter the excitability of the interneurons.
They do. They profoundly depress the traditional Ibn inhibitory interneurons. They effectively remove the brakes entirely.
Wow.
But more remarkably, this descending drive simultaneously depolarizes and opens a completely alternate parallel polysynaptic pathway.
So there's a hidden track.
A hidden track. And this newly accessible circuit writes the exact same IB sensory signal through a chain of excitatory interneurons that project back to the extensor motor neurons.
The reflex literally inverts.
It reverses completely. Now, when the foot hits the ground and the load on the extensor muscles dramatically spikes, the rapidly firing GTOs no longer cause autogenic inhibition.
Instead, that massive IB volley powerfully excites the extensor muscles.
Exactly. The greater the load applied to the limb, the harder the extensors push back.
That dynamic remapping is just a mechanical necessity. It allows the limb to automatically function as a shock absorber and a load-bearing pillar without requiring the motor cortex to consciously calculate the required extensor force for every single footfall.
Because if the cortex had to do that, you'd trip every 3 steps.
To use a quick mental model, think of a video game controller. When your character is on land, the X button makes them jump. But when the character swims underwater, the game software remaps the controls, and that exact same X button now makes them dive deeper.
That's perfect.
The physical button, the afferent hasn't changed, but the internal routing, the interneuron pool, has completely flipped the motor output based on the environment.
Yes. The hardware's the same, the software changes.
Taking a deliberate breath here, we have focused intensely so far on proprioception, the internal telemetry of length and force. But the spinal cord is also orchestrating whole limb kinematic responses to external threats.
Right. Because the world is dangerous.
It is. If our listener steps out of their car barefoot and steps on a piece of shattered glass, the spinal cord doesn't just manage one muscle. It coordinates a massive bilateral protective synergy. Let's look at cutaneous reflexes.
Okay, so the flexor withdrawal reflex. This is triggered by nociceptors in the skin, specifically the lightly myelinated adelta fibers conveying sharp, fast pain.
Ouch.
Right. And unlike a discrete stretch reflex, pulling a whole limb away from a noxious stimulus requires the coordinated flexion of the ankle, the knee, and the hip.
You can't just bend your toe.
Exactly. Therefore, when the A delta fiber enters the dorsal horn, it diverges massively. It sends collaterals rostrocaudally up and down across multiple spinal segments.
It activates a vast, distributed web of interneurons.
It does. And this interneuron web executes a widespread pattern of reciprocal innervation. It drives powerful excitatory potentials to the alpha motor neurons of all the flexor muscles of the injured limb, causing an immediate multi-joint withdrawal.
And simultaneously, through parallel inhibitory interneurons, it silences the extensor muscles of that limb, ensuring there's no mechanical resistance to the escape movement.
Right. But physics demands a counterbalance.
Because if you abruptly retract your right leg while you're walking, your center of mass shifts violently and you will collapse.
Which is why the withdrawal reflex is obligatorily linked to the crossed extension reflex.
The crossed extension reflex.
Yes. The nociceptive afferents also synapse onto commissural interneurons. These are axons that cross the midline of the spinal cord entirely, going to the contralateral ventral horn.
To the other leg.
Exactly. And on the uninjured side, the reciprocal logic is totally inverted. The interneurons strongly excite the extensor muscles and inhibit the flexors.
So as the right leg violently retracts, the left leg instantly extends and stiffens into a rigid weight-bearing pillar, catching your falling body mass perfectly.
And the spinal cord computes this complex bilateral postural adjustment in milliseconds, completely bypassing conscious cortical intervention.
That's wild.
Furthermore, the electrophysiology of these polysynaptic cutaneous circuits reveals a phenomenon called after discharge.
What's that?
Because the interneuron web is so extensively cross-connected, the action potentials literally reverberate within local loops. So even after the foot is removed from the glass and the adelta fibers fall silent, the motor neurons continue to receive excitatory drive for several hundred milliseconds.
The spinal cord actively holds the limb in the retracted position.
Yes, ensuring the threat is fully cleared before returning control to baseline parameters.
And from an evolutionary standpoint, the alternating rhythm of these exact reciprocal circuits, flexion on one side, extension on the other, this is actually the architectural foundation for the central pattern generators that drive rhythmic locomotion.
The building blocks of walking.
Yeah. But let's inject some conscious override into this system. Imagine I'm carrying a heavy cast iron skillet from the stove, and the handle is blistering hot.
burning your hand.
Right.
Okay.
The delta nociceptors are firing frantically. They're driving the interneurons to initiate a flex or withdrawal. But my cortex knows that dropping a pan of boiling oil onto my feet is a catastrophic outcome.
A much worse outcome.
Right. So I grip my teeth, I suppress the urge to drop it, and I carefully place it on the counter. How does the cortex veto an ancient hardwired spinal reflex like that?
Ah. The biophysics of that override rely entirely on the principle of spatial summation at the level of the interneuron.
Okay.
We really have to discard the idea that interneurons are just dedicated, private pathways for single reflexes. The reality of the spinal cord is massive convergence.
So they're multitaskers.
Yes. A single interneuron in the flexor withdrawal pathway doesn't just receive the nociceptive A delta input. It is heavily innervated by vast descending tracts from the motor cortex, the red nucleus, and the reticular formation.
It's a central switchboard, receiving excitatory and inhibitory votes from across the entire nervous system.
Exactly. The interneuron acts as a biological integrator. In your skillet scenario, the nociceptors are driving massive excitatory postsynaptic potentials, EPSPs, onto the withdrawal interneuron.
They can drop it.
Right. But simultaneously, your motor cortex sends a profound descending volley of inhibitory postsynaptic potentials, IPSPS, down the corticospinal tract directly onto those exact same interneurons.
Say, hold on.
Yes. And the descending inhibition hyperpolarizes the interneurons, effectively canceling out the peripheral excitation. The firing threshold is never reached, the interneuron remains silent, and the reflex is successfully muted at the spinal level.
You never even reaches the motor neuron.
Never even gets there.
That's incredible. The cortex doesn't have to micromanage the muscle to stop the reflex. It just unplugs the reflex arc at the interneuron.
Exactly.
And this massive convergence is really a hallmark of skilled motor control. The Candle text heavily features the research of Anders Lundberg and later Bror L. Ostermark and Tadashi Isa, and they focus on a highly specific population of interneurons critical for upper limb kinematics, the propriospinal neurons.
Yes, propriospinal neurons. They're unique because their axons do not exit the central nervous system to innervate muscle, nor do they ascend to the brain.
They stay local.
Right. They project entirely within the spinal cord, linking different segments together. And the crucial population Lundberg identified in primates resides in the upper cervical segments, specifically C3 and C4.
High up in the neck. What makes this C3, C4 population so functionally critical?
Well, their research demonstrated that these propriospinal neurons are the essential command centers for visually guided, multi-joint reaching movements, like reaching out to grasp a specific object on a desk.
Okay.
When the motor cortex formulates the intent to reach, it doesn't calculate the individual firing rates for every single motor unit in the shoulder, the elbow, and the wrist.
Right. The computational load would be staggering.
It would be impossible. Instead, the cortex sends a generalized command down the corticospinal tract, which terminates heavily on these C3, C4 propriospinal neurons.
It delegates the kinematic mathematics.
Precisely. These propriospinal neurons are heavily convergent. They receive the descending cortical intent, but they also continuously receive ascending proprioceptive data from the limb itself.
From the spindles and GTOs.
Exactly. They know the exact position of the elbow, the tension in the shoulder muscles. They integrate the top-down command with the bottom-up physical reality, compute the necessary muscle synergies, and then project down to the lower cervical segments like C6 to T1 to drive the specific alpha motor neurons required for a fluid, accurate reach.
It's an organizational masterpiece. The motor cortex acts as the CEO, issuing broad directive. And the propriospinal neurons act as local project managers, using real-time peripheral data to execute the CEO's vision smoothly.
That's exactly how it works.
But with all this massive convergence, thousands of descending and peripheral synapses bombarding the interneurons and motor neurons, the system has to require aggressive regulatory mechanisms.
Oh, absolutely, to prevent runaway excitation and filter out the noise.
Right. We need to examine how the spinal cord fine-tunes the signal. So let's look at Renshaw cells and recurrent inhibition.
Okay, Renshaw cells. These are small, inhibitory interneurons located in the ventral horn, anatomically right adjacent to the alpha motor neurons. And they govern a really tight negative feedback loop.
How does it start?
When an alpha motor neuron fires an action potential, it sends a signal at the ventral root toward the muscle, but before the axon leaves the spinal gray matter, it gives off a recurrent collateral branch.
Little side branch? That synapses directly back onto the Renshaw cell.
Yes. The motor neuron releases acetylcholine at that collateral synapse, which strongly excites the Renshaw cell.
Okay.
And the Renshaw cell, in turn, projects its axon right back onto the soma of the exact same alpha motor neuron that just excited it, as well as onto neighboring synergistic motor neurons. And it releases the inhibitory neurotransmitter glycine.
Wait, so the motor neuron literally triggers its own inhibition. It fires, and in doing so, activates a circuit that immediately tries to silence it. Why engineer a system that actively fights itself?
Because it functions as a precise physiological governor.
A governor.
Right. During a sustained voluntary contraction, the motor neuron pool needs to fire at a stable asynchronous rate to maintain smooth tension. But convergent excitatory inputs can be volatile.
They spike.
They spike. If a motor neuron begins firing too rapidly, it drives the Renshaw cell harder. The Renshaw cell floods the motor neuron with glycine, inducing deep IPSPs that slow the firing rate back down.
And if the firing rate drops too low?
Then Renshaw inhibition wanes, allowing the motor neuron to speed back up.
It acts exactly like a thermostat, smoothing out the firing frequencies, preventing tremors, and ensuring the mechanical output of the muscle is fluid rather than jerky.
Exactly. And crucially, descending pathways can synapse onto the Renshaw cells themselves to adjust their baseline sensitivity, allowing the brain to dial the governor up or down depending on whether the task requires explosive power or meticulous control.
That's brilliant. But Renshaw inhibition acts postsynaptically, right? It alters the overall excitability of the motor neuron.
Yes, it acts on the receiving cell.
But the Candle text places immense emphasis on a conceptually distinct, profoundly elegant mechanism for filtering specific data streams. Presynaptic inhibition. And for any neuroscientist, the biophysics of this mechanism are just absolutely stunning.
I agree. Presynaptic inhibition is arguably the most sophisticated modulatory tool in the spinal cord because in postsynaptic inhibition, you hyperpolarize the target motor neuron, and by doing so, you reduce its responsiveness to all incoming signals globally.
You just turn down the whole machine.
Right. But presynaptic inhibition is surgical. Specialized GABAergic interneurons bypass the motor neuron entirely and synapse directly onto the axonal terminal bouton of a specific incoming sensory fiber. For example, the eye afferent.
Just microns before it contacts the motor neuron.
Exactly.
It intercepts the telemetry at the absolute last moment before the synaptic cleft.
Now, let's dig deeply into the electrophysiology here because it relies on a paradoxical chloride gradient that always trips up students.
Oh, the NKCC1 paradox. Yes.
Right, because in a standard adult neuron, GABA is an inhibitory neurotransmitter. It opens GABA-A receptors, allowing chloride to rush into the cell, hyperpolarizing the membrane away from the firing threshold.
Normally, yes, but primary sensory afferent terminals possess a totally unique internal chemistry. They heavily express the NKCC1 transporter, which actively pumps chloride into the terminal at rest.
So it's hoarding chloride. Exactly. As a result, the intracellular concentration of chloride in the eye afferent terminal is unusually high. So when the GABAergic interneuron releases GABA onto the terminal, the GABA-A receptors open, and chloride actually rushes out of the cell down its concentration gradient.
And because negatively charged chloride is leaving, the inside of the terminal becomes more positive. It depolarizes.
It does.
This is the paradox. We're discussing presynaptic inhibition, yet the mechanism is a depolarization. Depolarization usually facilitates firing. How does a chronic, low-level depolarization inhibit neurotransmitter release?
The inhibition stems from the voltage-dependent kinetics of the sodium channels.
Okay, break that down.
A chronic, sustained depolarization alters the conformational state of the voltage-gated sodium channels embedded in the terminal membrane. It drives a significant percentage of them into an inactivated state.
So they are essentially locked out of participating.
Exactly. So when a true full-sized action potential travels down the eye afferent from the muscle spindle and arrives at this pre-depolarized terminal, the resulting action potential is severely blunted.
It shrinks.
The amplitude is significantly reduced because there are simply fewer available sodium channels to propagate the spike.
And according to the biophysics of vesicle fusion, a smaller action potential means a smaller voltage change at the terminal.
Yes. A smaller voltage change means fewer voltage-gated calcium channels open, specifically the N and PQ types. And since calcium influx is the direct trigger for synaptic vesicle exocytosis, less calcium means fewer vesicles fuse with the membrane.
The terminal releases significantly less glutamate into the synaptic cleft.
And the EPSP generated in the motor neuron is drastically weakened.
The cascade is phenomenally precise. To use a quick analogy, postsynaptic inhibition is like turning down the master volume on an audio receiver.
Yeah.
Every instrument gets quieter. Presynaptic inhibition is like being a sound engineer at a mixing board. The motor neuron's master volume remains perfectly sensitive to descending cortical commands, but the interneuron reaches over and pulls down the slider for just the bass guitar, just the specific IA afferent from one muscle spindle.
Filtering out the noise while leaving the rest of the kinematic data crystal clear. It's a perfect analogy.
Taking a deliberate pause here, we have mapped out an exquisitely balanced ecosystem. We have the raw latency of the stretch reflex, the sophisticated dynamic telemetry of the spindles, the phase-dependent remapping of the GTOs, the computational brilliance of propriospinal networks, and the surgical precision of presynaptic inhibition.
It's a masterpiece of biological engineering.
It is. But as any PhD student in this field knows, you only truly understand a complex system when you observe its failure modes. We have to examine what happens when this delicate spinal architecture is disconnected from the brain.
Yes, pathology.
Let's move into our final conceptual block: plasticity, pathology, and spinal shock. We know spinal networks are highly plastic. They physically remodel based on usage.
The plasticity of the spinal cord is undeniable. Jonathan Wolpaw's classic operant conditioning experiments definitively proved this.
Right.
He demonstrated that primates, and eventually humans, could be trained to consciously increase or decrease the amplitude of their monosynaptic H-reflex over several weeks, simply by providing rewards or biofeedback based on the reflex size.
So the spinal cord literally altered the baseline synaptic efficacy of the IA to alpha connection to optimize the behavioral outcome.
Exactly. But Wolpaw's critical finding was that this spinal plasticity requires an intact corticospinal tract. The descending pathways are absolutely necessary to guide and maintain the local interneuron remodeling.
Which brings us to the devastating clinical realities of spinal cord injury, SCI. When traumatic injury severs those descending tracts, the immediate clinical presentation is a profound state of hypoflexia and flaccid paralysis below the level of the lesion, known as spinal shock.
It's a total systemic shutdown.
Why does it happen?
It occurs because the spinal motor neurons and interneurons normally rely on a constant tonic background of excitatory facilitation from descending monoaminergic pathways, specifically serotonin and norepinephrine from the brainstem.
The background hum.
Right. And without that continuous descending drive, the resting membrane potentials of the spinal neurons hyperpolarize significantly. They become deeply unresponsive. You can mechanically stretch the spindle, the IA afferent fires perfectly, but the EPSP is completely insufficient to bring the hyperpolarized motor neuron to the threshold.
But the nervous system abhors a vacuum. Spinal shock is transient. Over weeks and months, the condition evolves into a severely maladaptive state of hyperexcitability known as spasticity.
Right. The pendulum swings completely the other way.
The reflexes return, but they return in a wildly exaggerated, chaotic manner. Patients develop severe hyperreflexia, where just a mild tendon tap induces clonus, a massive, oscillating spasm.
An intense muscle tone, violently resisting passive stretch.
So what are the specific cellular mechanisms driving this transition from silent to hyperactive?
Spasticity is driven by a cascade of maladaptive plasticity. As the isolated spinal cord desperately attempts to restore its baseline excitability, three main things happen. First, there are profound changes in the intrinsic biophysical properties of the motor neurons themselves.
Okay.
Deprived of monoamines, the receptors become supersensitive. The motor neurons heavily upregulate voltage-gated calcium channels like Cav1.3 and persistent sodium channels in their dendritic trees.
These ion channels mediate persistent inward currents, PICs.
Yes, and the upregulation of PICs means that a tiny, brief sensory input can trigger a massive self-sustaining depolarization in the dendrites. The motor neuron develops a plateau potential where it locks into a state of continuous high-frequency firing long after the initial sensory stimulus has ended.
Driving the muscle into a relentless, rigid contraction.
Exactly. Second, there is structural reorganization, collateral spreading. Because the severed descending axons degenerate, they leave vast arrays of empty synaptic targets on the motor neurons and interneuron.
Yes, real estate opens up.
Right. And the surviving peripheral sensory afferents, particularly the IA fibers, sprout new axonal branches and aggressively innervate those vacated spaces.
So the synaptic density of the sensory afferents increases dramatically. A standard muscle stretch now delivers a significantly magnified excitatory volley to this already hyperexcitable motor neuron, triggering an exaggerated reflex.
Yes, but the most devastating driver of spasticity relates directly to the regulatory mechanisms we just discussed. The profound loss of presynaptic inhibition.
Oh, wow.
The GABAergic interneurons that mediate presynaptic inhibition on the IA terminals are heavily driven by descending pathways. Following transection, that descending drive is permanently lost.
The sound engineer has left the mixing board.
The sound engineer is gone. The chronic depolarization on the IA terminals vanishes, the sodium channels recover, and the afferents are suddenly transmitting at maximum biological volume.
The sensory filtering is completely destroyed.
Completely. The slightest movement, a change in posture, or even just the brush of clothing against the skin triggers massive, uninhibited afferent volleys that crash into supersensitive motor neurons prone to plateau potentials. It is a perfect storm of sensory overload, resulting in chaotic, involuntary motor output.
And for the PhD student analyzing these mechanisms, it forces a critical evaluation of current neurorehabilitation protocols.
Huh.
I mean, if the isolated spinal cord is actively reshaping its own ion channel distribution and sprouting new synapses, physical therapy cannot simply be about preventing muscular contractures.
No, not anymore. Modern rehabilitation paradigms, such as intense locomotor training on treadmills with body weight support, they treat the physical therapy as targeted sensory input.
Retraining the cord.
Exactly. By forcing the limbs through the highly structured rhythmic kinematics of walking, therapists are driving organized, phase-appropriate sensory volleys from the spindles and GTOs right into the spinal networks.
The goal is to harness the intrinsic plasticity of the cord, using rhythmic sensory feedback to guide the interneuron webs to rewire themselves toward functional central pattern generation, rather than settling into the chaotic loops of spasticity.
It's using the body's own telemetry to debug the corrupted software.
It is a phenomenal area of active research, and it beautifully synthesizes everything we have unpacked today. Let's take a final step back and look at the ground we've covered. We began by dismantling Sherrington's convenient fiction, proving that the monosynaptic reflex is heavily regulated. We explored the exquisite dual-action biophysics of the muscle spindle and the continuous tension telemetry of the Golgi tendon organ.
We examined the software updates of state-dependent reflex reversal during locomotion, the massive convergence and kinematic calculations performed by propriospinal networks, and the surgical precision of presynaptic inhibition acting on the sensory terminals.
And we closed by observing the raw, devastating power of spinal plasticity when that architecture is isolated following injury. To our listener driving right now, remember, this is just Chapter 32. This is just the bedrock. In our next session of this Candle Part V series, we will build directly on this spinal foundation as we ascend into the brainstem, central pattern generators, and the higher cortical centers of motor control.
It only gets more complex from here.
It really does. But before we sign off, I want to leave you with a final provocation to mull over as you finish your commute. We routinely use the phrase muscle memory. We treat it as a comfortable metaphor, assuming that the memory of how to execute a flawless tennis serve or perform a complex piano sonata is housed entirely within the synaptic waste of the motor cortex or the cerebellum.
Right, all in the brain.
But given the profound plasticity, the massive multisensory convergence, the independent computational power, and the ability to dynamically rewire pathways based on behavioral intent that we've just seen in the spinal cord, is it possible that a highly significant portion of what makes an elite athlete or a virtuoso musician isn't in their head at all? Is it literally physically encoded in the microscopic plastic interneuron webs of their spinal cord?
That is a fascinating thought.
Let the biophysics of that sink in. Drive safely, good luck with your doctoral research, and we will see you next time on our deep dive.